Greetings, differential equation fans, talking today about the convolution in Laplace transforms. We'll start off with a little bit of motivation for this question. The idea of looking at convolutions of the idea of looking at the inverse Laplace transform of things we recognize. We'll see how the convolution comes into play in a special way, and we'll see how the convolution can be used to solve initial value problems. At the end of the day, we'll also see how this convolution idea can be applied to integral equations too, which is a little bit different but related to the differential equations we've been solving. So as a motivating question, I'll point out that we frequently use the fact that the Laplace transform and its inverse are linear operators, right? So the inverse transform of a sum is the sum of the inverse transforms, and the inverse transform of a constant times something we know how to invert is just the inverse transform of that constant. Is the constant times the inverse transform of that thing we know how to invert. So here's a question, what about the inverse transform of a product? So it turns out these come up pretty often, and it turns out that when the transform of little f is big F and the transform of little g is big G, the transform of f times g is not big F times big G, or in other words, the inverse transform of f times g is not little f times little g. So don't do it. It's not correct. But in any case, this inverse transform does turn out to be related to the convolution. So we'll see that in a moment. Okay, but in any case, for a little bit more motivation, go back to a problem we already solved. So here is an initial value problem, a first order initial value problem, for which we saw the solution was a combination of exponentials, cosines, and sines. So along the way here, we actually saw that the transform of the unknown function here can be written as this function 2 over s plus 1 times this function, which is s over s squared plus 4. In other words, the transform of the solution is equal to the product of two transforms we know, namely 2e to the minus t times the transform of cosine t. Now, of course, the inverse transform is not the product of those transforms, so you can see right away that products invert differently when it comes to the transform. Okay, so start with a definition of a convolution here. The convolution is an operation that's defined when f and g are defined greater than 0. So f convolution g, f star g, is an integral. It's the integral of f of tau, g of t minus tau d tau. Okay, so you can think of this just as a new way to multiply functions. So here are two perfectly good functions, sine of 3t and 1. So let's go ahead and find f star g for these two functions. So just amounts to computing a definite integral. So in this case, f of tau is sine of 3 tau, and of course, if g of t is 1, g of t minus tau is also 1. So here's the convolution, right? It's just the integral of sine of 3 tau d tau. Integrates quickly with a quick u substitution, and we can see here that we end up with 1/3 times 1 minus cosine of 3t. Okay, of course, we could look at the convolution in the other direction too. Let's find g star f, and g star f just switch spots here, right? So to compute g star f, g of tau is 1, and sine of, f of t minus tau is sine of 3t minus tau. A substitution here to remove the t minus tau part. And then it turns out we end up with a familiar looking integral that integrates actually the same as before, right? So you can see that for this particular set of functions, this is equal to f star g. So you might be asking, is the convolution always commutative? And it turns out it is, and you can prove that. It's pretty quick to prove just using the same u substitution that we just used. Okay, so the u substitution here takes us from g of tau to g of t minus u, and it takes us from f of t minus tau to f of u. Of course, there's a factor of minus du, and the limits are backward. So switching those limits, we end up with exactly the definition of f star g. Okay, so g star f is f star g. That's sort of a reassuring factor of this convolution. So as I mentioned before, it turns out that the Laplace transform of the convolution is the product of the individual Laplace transforms. Now, the proof of this is a little bit beyond the scope of our class, but for those of you who have had multivariable calculus, the proof of this amounts to be a double integral over an infinite slice of the plane. So here we think of R as being the interval from tau from 0 to t, and then from 0 to infinity on the t-axis, right? So it's this interval. Now, a popular Calc 4 trick is to reverse the limits of integration, and when we do that in this case, we see that this region R can also be represented this way, right? As interval from tau to infinity, and then an interval on t from tau to infinity also. So this is t equals tau, and this is t. Okay, so with that said, we can actually reverse the limits of integration. So we see that here compared to this. And once you do that, the integrals separate into two distinct integrals with a u substitution. So the u substitution is u equals t minus tau. We end up with these two different integrals in two different variables, one of which is the Laplace transform of f, and the other of which is the Laplace transform of g. Okay, so the Laplace transform of the convolution of two functions is the product of the individual Laplace transforms. This is a pretty miraculous result. It also means we have a new inverse transform, right? So here is the inverse transform. The inverse transform of a product of two transforms we know turns out to just be the convolution of those functions. Okay. So a couple examples dealing with this. Let's go ahead and find the inverse Laplace transform of this mess here, 2 over s times s squared plus 9. So we can rewrite this as a constant, 2/3, times two Laplace transforms we know, right? 1 over s turns out to be the Laplace transform of 1, and 3 over s squared plus 9 ends up being the Laplace transform of sine of 3t. Now once we do that, the inverse transform is just going to be 2/3 times the convolution of 1 with sine of 3t. Now we actually found that in a previous example, right? We found that to be 1/3 times 1 minus cosine of 3t. So incorporating the factor out front of 2/3, we end up with the desired inverse transform, 2/9 times 1 minus cosine of 3t. Okay. Another example, here we'll go ahead and find the forward transform of something that can be expressed as a convolution. So here is e to the minus quantity t minus tau times sine of tau, all integrated from 0 to t, right? That's just the convolution of e to the t with sine of 3t. So if we want to find the Laplace transform of that integral, it ends up just being the product of the two individual Laplace transforms that you see here, right? So 1 over s minus 1 is the transform of the exponential function, and 1 over s squared plus 1 is the transform of the sine function. Okay, so a few examples solving initial value problems with these convolution operators. Start off with a comment. The first comment is that we sort of make liberal use of the fact that the t minus tau and the tau are interchangeable because f star g is g star f. Okay, so we'll see that in some examples that a lot of times we express f star g as integral of f of t minus tau g of tau d tau. Okay. And then what we'll see here is that the convolution is a useful way to express the solution of initial value problem, especially when you have an arbitrary source term. So an example where we solve an initial value problem here is x double prime plus x is sine of t with 0 initial conditions. So start off by transforming the initial value problem. So here's the transform of the left-hand side, and similarly the transform of the right-hand side here. Okay, so if the differential equation is x double prime plus x is sine of t, the transforms of those two must be equal, and it's quick to solve for the unknown function, the transform of the unknown function, which we see in this case is a product of the transform of sine and the transform of sine. So we can go ahead then and express the solution of this as a convolution of sine with itself, right? So here's the convolution theorem applied to these two transforms of sine. The solution is integral from 0 to t sine of t minus tau, sine of tau d tau. More generally, if we have a similar differential equation with an arbitrary source term, here the arbitrary source term is f of t, we can similarly express the solution of this differential equation with a convolution theorem. Okay, so I won't go through it, but the left-hand side and the right-hand side transform such that the unknown function capital X satisfies this equation, which we can solve quickly for capital X of S. And here I've just done one manipulation to multiply and divide by this constant omega, so that this looks like the transform of a sine function, and so does that. Okay. Therefore, the inverse transform just looks like x naught times the cosine plus x naught over omega times the sine times this convolution operator, right? So this is just 1 over omega sine convolution f. Okay, so this is a pretty cool way to express the solution as convolution operator. Now, that integral should remind you of something. You should notice that the structure of the solution here looks somewhat like solution to a homogeneous equation plus a particular solution. And no big surprise, it exactly is. So the solution here, I'll think about this as being the particular solution, and we'll go ahead and explore that term a little bit more. So I'll remind you that in a previous video when we had a look at variation of parameters, we saw that that the particular solution to any old non-homogeneous differential equation can be written in terms of the fundamental set of solutions for the corresponding homogeneous equation. Now here I'll do something kind of new and write these functions u1 and u2 as definite integrals instead of indefinite integrals. And the reason that we want to do that is because when we go ahead and write the particular solution as u1x1 plus u2x2, it turns out we can write that all as one integral. Okay, so I'll suggest that you go ahead and pause the video and just verify this, but we can put this combination of x1, u1, x2, u2 that you see here together and scrunch things down into just one integral. Again, here the variable of integration is tau, and I'll just invite you to compare this to what we saw just a moment ago, where the particular solution was written as the form g of t minus tau, f of tau, d tau. So it turns out that this thing here is exactly that function g from the right-hand side. Pretty cool, huh? So in order to see that, we'll go ahead and explore our example here, that particular solution, the Green's function, x1 of tau, x2 of t, minus x1 of t, x2 of tau, over the Wronskian. Oh, by the way, that's the same Wronskian from before. It has 0 initial conditions. So it's quick to see that when you plug in 0 here, we end up with 0, right? So it satisfies x of 0 is 0. And it turns out that the derivative also has 0 when t is 0. Okay, so in order to see that, just take the derivative. It requires a little bit of a Leibniz rule. It's quick actually to see that g of t and t is equal to 0, and it's also quick to see that when you plug in 0 to this integral, you get 0. Okay, so we often say that this Green's function is the particular solution that satisfies a non-homogeneous differential equation with homogeneous initial conditions, right? So again, x of 0 is x prime of 0 is all 0. So in this particular case, we'll go ahead and return back to this differential equation with the arbitrary right-hand side except with homogeneous initial conditions. And we've seen previously that with those homogeneous initial conditions, the solution x of t can be written as this function. Okay, so exploring that a little bit deeper, the Green's function for this particular equation using the fundamental set of solutions turns out to be this combination of cosines and sines, which, through the magic of a trig identity, we can actually write as exactly this function. So it turns out that this sine and this combination of sines are the same. Okay, so that's a pretty cool deal here that our investigation of variation parameters before comes back in our convolution operator here. Okay, so as a final thing, we'll go ahead and just close with the investigation of integral equations. So we saw previously in chapter 1 that we could solve integral equations of this form by first converting them to an initial value problem. So here we notice that the integrand reminds us a lot of a convolution. So we can express this integral equation actually as a convolution type of equation where x equals x of t is an unknown function. Okay, so since we know how to transform convolutions, the Laplace transform here turns out to just be, again, another algebraic equation in x that we can solve quickly for the unknown function. And so long as we can invert this this transform, we can get back the unknown function little x, which is the solution of the differential or the integral equation. So here's an example that illustrates that. Let's go ahead and solve this integral equation. X is e to the minus t plus the integral from 0 to t of x of tau d tau. Okay, so this doesn't look a whole lot like a convolution. It is. It turns out you can think about it as a convolution of x with 1. Okay, so transforming that equation, here's a Laplace transform, we can see that we have an algebraic equation for the transform of the unknown solution, which algebraically becomes this form. Just move this x of s over s to the left-hand side, factor and solve and simplify. And as it turns out, this is exactly the transform of the hyperbolic cosine function. Okay, so there is your solution of this differential or this integral equation, just cosh of t. Okay, folks, hope you have enjoyed this video on convolution operator. We'll see how convolution operator comes up again. We talk about impulse functions in our next video. So long for now. Take care. Bye-bye.